Okay guys, this is going to be a little bit different, but this is our virtual lecture since I'll be out of town today. Um, I'll be looking offside the camera quite a bit because I've got my screen up over here. My webcam's on my laptop, but my laptop's hooked up to my monitors on my screen, so you'll be able to see me in the corner and what I'm doing on the computer. Anyway, in the course, if you look in the course, there is a new learning module titled Normal Stress and Shear Stress that you can go into, but we haven't quite finished with the Introduction and Statics module yet. So if you go into the Introduction and Statics module, what you need to do in order to finish it off is download these statics examples. They're in PowerPoint presentation format. You'll need to reference these as you watch the statics example videos 5.1 and 5.19. This is just a quick refresher on statics. Make sure you go through that, and all in all, I think that takes about 26 minutes or so, something like that. But make sure you go through those because I want to make sure you guys are up to speed on statics, and if I remember right, I kind of tie it into strength of materials. So watch that in order to finish off the module, pardon me. But then after that, go into the new module, which is normal stress and shear stress. Let me click on it and go into it. And there's a lot of stuff here. There's a presentation which I'm going to go through now, but make sure you download that so you can look at it if you want. I guess it'll be on the video, so maybe it'll be high enough quality. But anyway, after that, there's a bunch of videos you need to watch. They're direct normal stress, direct shear stress, punching shear, statically indeterminate, axial deformation, tensile failure, punching, sandcastle holds up a car, interactive double shear is not a video, but all the way down to the sandcastle. You need to watch all of those. The first few videos are videos that are from the textbook, and they're very good. They're CAD models and very well done. The voice is a little boring, but good information, so make sure you watch those. Also, there's Chapter 1 example problems, which are the PDF solutions to the example problems that I work. You can download those and look through those, but I would just reference those as you watch the videos where I actually work through these. So that's example problem 1-37M, 1-49E, etc., all the way down to 1-69.M. Make sure you watch all of those videos. Those are the examples that I would have worked in class had I been there, but they are recorded from previous classes. So make sure you watch these. These are critical. These are how you're going to learn. So with all that being said, now hopefully you know what you need to go through in order to accomplish this learning module. Of course, there's a homework set at the end, and there's quizzes and things associated with this. Is there a quiz for one? Let's find out. I think there's a quiz. Quiz 1 and 2. You know what? I don't have it in the learning modules. So there may not be a quiz, but if there's a quiz, I'll add it in here in the list, and you'll see it appear by the time you are looking at this. Anyway, let's go into the presentation. I've already got it pulled up here. So what we're going to do is talk about normal and shear stress. These are two different types of stress. It's really important that you understand the two. Hope I don't need a whiteboard. I'm recording this in my office. We'll see. So quick overview. We're going to talk about stress, stress units, direct stress, and direct shear stress. Those are the things we're talking about. So basically, what is stress? Well, it's internal resistance to a load. It's another way of thinking of it is the way that the material actually resists the external load, how that load is divided up into the material so that all of the material helps in supplying that load or in supporting that load. I had an idea just yesterday when I was thinking about the lecture for today, and I thought of just a broom. Imagine a broom like you'd get for decoration purposes that's just not really for use, but it's just straw and it's in a bundle, so about so long, just a round bundle of straws. If you think about grabbing a hold of that bundle and trying to pull it apart, it would be very difficult. So the force that you're applying, you can add a load cell or something between your hand and the broom, but you could measure the amount of force you're applying to try and pull that broom apart. Now, each piece of straw, if you were to take one piece of straw and pull it, apply that same force to it, of course it would fail. But when all the straws are equally taking this load, then it's much stronger. The amount of force per straw is less, and that's really what we're talking about here, is force per unit area. Okay, so Now, instead of it being one straw, we're talking about, say, 1 square inch of area. If you imagine a solid round cylinder of steel that you're trying to pull apart or that's supporting a load, and you can imagine cross-sectioning that steel, and you'd see the round cross-section. You can calculate the area once you measure the diameter, just as pi r squared. And what we're talking about is each square inch then taking a certain amount, a certain percentage of the load, a certain fraction of the load. So stress is just how much force the entire member is taking divided by the total area of that member. Hopefully that makes some sense. And I think you've dealt a little bit with stress before, so hopefully you understand what this is. As I said, it's a lot like pressure. It's a lot like pressure in a fluid where you have force per unit area. That's all stress is a force per unit area. All right, so stress could be uniform across the section of a member. If you think about a member in a bridge, an I-beam or something, it may be that every point, if you imagine cutting that I-beam and looking at each point, it could be that every point has the exact same amount of stress. In the real world, that's not really what happens. The stress actually varies across the cross-section. The stress at one point will be different than the stress at another point in the cross-section. And depending on the type of load, that variance can be quite a lot or it can be a little bit. A lot of times we're just interested in the stress at a single point because what we really want to do is find out what is the highest stress, say, in a cross-section, because that's the point where the material is most likely to begin failing. Materials, of course, do vary. Materials are not perfect. You might make an I-beam and the top plate is stronger than the bottom plate because the bottom plate has some inclusions, or maybe the alloy is not quite right there. We're ignoring that right now. What we're thinking about is how much does the loading vary along the cross-section, not just where is the material weakest. We're going to just use an average material property and then put a safety factor on top of it. But anyway, we're interested in stress at a point because we're interested in what point has the highest stress. Pardon me. Since that's the point where failure will likely begin. All right, so here's an example. It's a simple bracket. You may have one like this in your home. It probably doesn't have as high a load as this bracket has, but anyway, this is a bracket that would be affixed to a wall of some type. So there's two bolt holes, one at the top and the bottom indicated here, and then there's a force out at the end of the bracket that needs to be supported. Now, if we plug this into a finite element analysis package, we can actually find the point where there is a higher stress. And what you notice here is that the stress is not the same throughout the member, right? Okay, now, that doesn't tie in real well with what I was talking about before, a bridge and a cross-section, a member, a two-force member, but you get the idea that the stress may vary throughout the body, and we have to somehow deal with that. So this is a non-uniform stress case. Now, what units will we use for stress? Well, in the English system, it's PSI. It's actually the same units as pressure, or KSI, which is thousands of pounds per square inch. In the SI system, we'll use newtons per square meter, or pascals, megapascals, and actually gigapascals, which are not included here. You might want to write this down. If you like taking notes, here's your chance. A gigapascal is something we're going to use quite a lot, and it's a kilonewton per millimeter squared. It transforms nicely to other things, and that's why we use it so much. But anyway, so there's our units. They're same as pressure units. Now, various materials have different strengths. Some materials can take higher stress than others and not fail. I just watched a video. You know, I should post this for you guys. I'll probably include it in Machine Elements, but I just watched it last night. It was some people in Russia, and they had a nice shop, and they decided to do something crazy. They took the springs off an old car, the rear springs. They were just coil springs, and they decided to remake them out of rebar and see if rebar would be a decent material for rear coil springs on this car. So they basically just matched the geometry. The rebar was about the same diameter as the coil wire material was, and they found a mandrel, basically just a column that they could wrap it around. It was kind of interesting. If I get the chance, I'll find it and post it for you guys so you can see it. But anyway, so they made these coil springs and ended up getting a process where they were pretty close in geometry to the original springs, and they put these springs in the car, drove down the road. Of course, what eventually happened was the springs collapsed on themselves, right? They worked for a while. It started off, the car was really jacked up in the back. It was way off its normal height, but in the end, the wheels were just sitting on the inside wheel wells, basically, and it was completely failed. But that should give you the idea that just because something's metal doesn't mean it's going to have the same properties, and you know this from your materials classes, but there's quite a variation. In fact, what was happening in that example was that the material was yielding. It was permanently deforming, right? Because they started out with the right shape, and as the material moved, it didn't completely move elastically. It moved plastically. So in other words, it got some permanent set in the spring. The springs changed their geometry. So here's some, and you should be following along in the slides if you can't read them in the video. But anyway, so here's some representative numbers for yield strength, ultimate strength, and density for some various materials. We start off with a common steel, a carbon steel, which has a higher overall ultimate strength, human skin, for example, titanium. And you can kind of see the variation in properties between all these materials, and you notice they're all different. Diamond is extremely strong, but of course it doesn't make sense to make a bridge out of diamond. That would be ridiculously expensive and probably impractical. All right, so when we talk about direct normal stress, I don't know why I have an apostrophe or a parentheses S there. Maybe stresses. I don't remember why I put that there. But anyway, when we talk about direct normal stress, we're talking about one of the simplest cases of stress. We're talking about the case where the stress is normal to the cross-section. So if you look at the picture here, we've got a body that we're going to imagine separating into two free bodies. And so from statics, you should realize that the force applied externally to this body would be the same force internally. It has to be for these two to be in equilibrium. But then that force would be, in reality, divided up over the entire cross-sectional area. All the cross-sectional area works together, kind of like those straws in a broom, to hold the material together and prevent it from failing and fracturing at this line. So over here in the last picture, we've got several different small arrows indicating force per unit area that's operating together to hold this material together and make it not fall apart. Well, when we assume that this stress is uniform across that entire cross-section, then this is a direct normal stress. This is a very, like I said, the simplest example of stress. Now this is a tensile example, but the stress could be in compression instead, so tending to crush the material and the object. Now, here's our first symbol that you've probably not seen. We use the symbol sigma to represent stress, and it's just force per area. So if we know how much force is being applied and we know how much area is available here in the cross-section to take the load, we just divide the force by the area, and now we have the magnitude of the stress. Now, in direct normal stress, the area of the cross-section is always perpendicular to the applied force. Otherwise, we're talking about a different kind of stress. And there is another type, which is shear, and we'll get to that in a moment. Now, you've probably pulled apart a dog bone in another class by now, and if you have, you probably noticed that the dog bone necked down as it was being pulled apart. And what you may not have thought about was the fact that as the dog bone is pulled apart, it's necking down, and the actual area available to take the load is decreasing, right? It's changing shape, it's changing size, there's less area there, and so the stress actually increases as you continue to pull the dog bone apart. However, in tests like that, we always reference the original cross-sectional area in calculating the stress. So anyway, you may have also noticed that your metal samples broke at an angle. There was always an angle there. You may wonder why. We'll get to that later in the course. All right. It's not because the plane is not horizontal. We can still imagine a horizontal plane where we're directly pulling the material apart. All right, so we can talk about normal stress elements, and the idea here is if we can think of stress as force per area, could we get smaller and smaller? Could we take imagine a round cross-section, could we just keep zooming in farther and farther on that round cross-section till we get to a point? So we consider a stress element that is an infinitesimal thing, right? A zero size thing where we can still talk about the stress on the element. Why would we want to do that? Well, there's many reasons. We'll get to them later. But for right now, just understand that we want to start thinking about points where stress exists. All right, so when we talk about stress elements, we're talking about something that has zero size, something that exists at a point. And this is really important because if you think about it, if you think about the round cross section where you have direct normal stress, you could keep zooming in farther and farther. We don't have to talk about just, say, 1 square inch of area and how much force there that square inch is applying to hold the material together. We could keep zooming in until we talk about a point, and an infinitesimal point will still have stress on it. And you can think of that stress sort of as a force because of the area on either side is the same, so the forces on either side would be the same, and it has to be for the element to be in equilibrium. And as long as the material is not coming apart, every element, every single point inside of the material has to somehow be in equilibrium. This concept will be very, very useful for us as we go along. So the first case, A, we've got a 3-dimensional stress element. In reality, all elements are 3-dimensional, but sometimes we'll simplify it down where it looks like B, where we have a 2-dimensional stress element. And these elements could have compressive or tensile stresses on any surface. We've just shown a compressive stress and then a tensile stress on the upper and lower surface, but really it could be on any surface. Now understand that on opposite faces, the stresses have to be the same for the element to be in equilibrium. All right, so let's talk about direct shear. We've talked about direct normal stress. Now let's talk about direct shear stress. This is a different type of stress. In this case, what's really different is that the direction of the load is along the same direction as the face. What do I mean? Well, if you imagine a test fixture here where we're trying to test the strength of a block of wood by loading it, so we're breaking it along the grain, which is the weakest direction for the wood, you can imagine that the area that's being stressed is a rectangular area that is the same shape and size as this area out here that's labeled C. You see the dimension C, but also you could look at that as a label for the face. Anyway, that same area would be back here, and that's the area that's being stressed. Now you notice that area, or the force, lies along that surface, right? So this is a different type of thing. Before, the surface we imagined was at a right angle to the load, okay? Now the direction of the force and the direction of the surface is exactly the same. So we've got, another example is this punch being punched down through a fairly thin piece of material. In that case, there's shear stress on the surface here that's being punched out. The direction of the load and the direction of the surface is the same. If my hand represents part of that shape, the direction of the load lies along the direction of the surface. So it's like a cutting action. This is actually what scissors do. It's a shearing action where the direction of the force and the surface being cut or being cleaved is in the same direction. In that case, we use a different symbol. The units are still the same. We're still talking about stress, but it's a very different kind of stress. So in that case, we talk about shear stress, and we use the symbol tau. It looks kind of like a T, but it's a Greek letter. And it's just the force divided by the shear area rather than the normal area that we had before, rather than the normal cross-section. This is kind of similar to direct normal stress in that we assume that the shear is the same magnitude everywhere. Wherever the material is being sheared, we assume that shear magnitude is the same. Otherwise, it's not direct shear stress. Now, shear in real bodies can vary throughout the body, but in our beginning case here, in the simplest examples, we assume that the shear is the same everywhere. And the key is that the area that's being sheared is in the same direction. It's parallel to the applied force. Now, where would we see this? Well, if you have a pin holding something together in a machine, holding links together, there's certainly shear operating. So here we've got a reaction force and a force on a link that's connected to a base by a pin. And you notice that this plane down here is a place where the pin could fail. The pin, if you imagine, I don't know, something like this marker representing that pin, and the two elements, or the two links holding onto it, it's literally trying to shear it, trying to break it in half, cut it this way by a load applied this direction. We're not talking about a direct normal stress like this with the load perpendicular to the face. We're talking about a shear stress where we're trying to push it and trying to shear the pin. Okay, so it's a different kind of stress than a normal stress. So this is an example of shear stress. Frequently, though, when you have a pin, what you'll see is double shear, where like in the lower graphic here, the pin connects the link to the base in two places, and so there's two cross-sectional areas that are involved in shear. There's a couple of reasons for this. Number one that you'd probably realize is that you end up with twice the area, so twice the load that can be supported. But the other reason is, in this case, there's actually also a moment load that is much more damaging than the shear load. So double shear is more common. It's just stronger overall and is a good idea. So it's, like I said, more common. All right, here's a shear on a pin. We've zoomed in on a pin where you can see the shear area. You can see that the force now is no longer along the axis of the pin. The shear is above and below the area, and you can see the shear stress itself that lies along the face that we're trying to shear. This is an example. I won't go through it. It is in your book. I'll let you go through it. The examples I work are examples from the back of the chapter. I prefer to work problems more like your homework problems. I feel like it's fairer, or I feel like you get more out of it, I guess. So you can go through this if you want. It's in the text. I've just left it in because I've forgotten to take it out, honestly. I would leave this one in on purpose because this actually relates to machine elements, which I also teach. And I really like this because it helps you understand how keys work, a key in a slot. Basically, the key is under a shear load. If you think about it, here's a key here, but this plane that's been highlighted in the center of the key is the plane that is under load where there is significant shear stress trying to shear the key apart. So this is another example. Again, you can go through that in the text. Let's see. Now, when we think about the element we talked about before, the shear or a stress element, not only could there be normal stress, so that was the sigma coming off of the face, there can also be shear along the face. Okay, so there can be shear stress on the surface of the face as well. Now, if you think about what has to happen, let's look at the shear element in a two-dimensional view to keep it simple for now. If you think about a point in the material having shear on it, imagine that the line at the top of this shear element is the surface from here. Okay, so we're just zooming in on a little bitty point. There's shear stress on that surface. If that's this shear stress here at a point, well, how would we keep this element in equilibrium? How would we keep it from moving within the greater bulk material that it's part of? Well, the only way to do that is to put an equal and opposite force on the other face. The problem is, if we put a shear in the opposite direction, there's going to tend to be rotation of this little infinitesimal bit of material. So we have to have shear stress on the other faces as well that tend to cause an opposite moment to keep the thing from rotating. So to keep the element in equilibrium and to satisfy statics, because we can apply statics to little bitty pieces of material that are actually inside of larger bits of material, if we're going to have a shear force here and an opposite shear force here, we have to naturally have these other two shear forces. So shear force never exists by itself. There's always, if you imagine an infinitesimal point of material, there's always these other shears as well that are generated as a natural byproduct of that one shear stress. Kind of interesting. There are other types of stress besides normal stress and shear stress. There's also bearing stress, which is a special type of normal stress. But basically, bearing stress is where you've got objects sitting on one another. If you imagine just setting your hand down on a table and supporting your weight on your hand, that's an example of bearing stress. Here's an example of a bone where you've got a socket, and there's certainly bearing stress there. Usually there's a large area of contact, and frequently the way it works is that when we're talking about bearing stress, we're usually talking about a non-uniform distribution of stress. So there's an integrated stress over an area that gives rise to a bulk force, but there's pressure variation. That's what they're trying to illustrate here with these colored graphics, is the distribution of stress along the contact area. You can think of this think of a ball bearing, for example, where there's a spherical ball, a spherical rolling element, and theoretically the contact is simply a single point. But in reality, since no material can resist infinite stress, and remember stress is force per area, and if the area is zero, well, that's infinite stress, Well, since no material can resist infinite stress, the ball literally has to flatten out some. Imagine a beach ball sitting on it, okay, or an exercise ball, and how the bottom of it must flatten out somewhat to have a contact patch to support the bulk load. So the same thing happens on any material where there's theoretically a point of contact, but what you end up with is a non-uniform distribution of stress along the surface. And all of that is actually very interesting, very relevant to bearing design, but we'll talk about that more in machine elements. Don't forget to take breaks if you need to in this video and rewind to watch more of it or watch parts of it again if you don't understand anything. And of course, feel free to ask me questions when I get back. Contact stress naturally arises from bearing stress. Usually it's a small area of contact. Think of a cylinder on a flat surface or a sphere. Usually we're talking about a point or line contact. So there's a lot of overlap between bearing stress and contact stress. But in bearing stress, typically there's more contact at the beginning. In contact stress, there's very little or theoretically zero contact or a point contact. Oh, I threw this in because it was really interesting. How did it tie in? I'm trying to remember now. I should have reviewed these slides before making the video. But I have a problem at my house where I've got a driveway, and it's just a gravel driveway. I've got a pond on one side, and the pond, when it overflows, it drains under the driveway. Well, the culvert under the driveway for a long time has really not done well, hasn't done its job, and frequently what will happen is water will flow over the top of my driveway in one particular area, and it's just horrible. It'll just wash out the driveway every time. I find gravel in my yard, and it's just a big pain. And so I decided, hey, I want to build a nice looking bridge. I still haven't got it done yet, but I have a couple of real good ideas, I think. And it turns out that Texas A&M had some footings information. You might want to follow this link. It's pretty good. But it's really interesting because if you want to support a bridge, what is a bridge? Well, a bridge is something that takes a load that normally is basically right in the middle of the air and moves the support for that load out to two other points. In this case, it's moving it out. You can see it over here and over here. Well, these are called footings. And if you think about how a footing works, a footing has to sit on ground, right? Well, ground or mud or dirt or whatever, sand, whatever you have, is not all that strong. You can poke your finger down into it, right? I mean, you can kind of dig around with your hands and make some progress. So how do you put a material on top of that is supposed to then take a force and distribute that force over an area, so make it a contact or a bearing stress? How do you do that well? And this reference gives some information on how much stress various soils can support, so that way you can decide how how big your footing needs to be. So if you know the weight of a vehicle, like for example, I'll want a concrete truck to be able to drive over this bridge. If that's what I want, that determines the size of the footing that has to spread out the load from that concrete truck, so that I don't apply too much force to the ground and the footing then sink into the ground. Of course, the added problem is that I'll have water running under here and constantly trying to wash out the footings. So I've got to figure out how that's going to work. All right, so in summary, stress is internal resistance of a body to an applied load. Stress is force per area. That's the dimensions. Those are dimensions, pardon me, of stress. And normal stress, the key to remembering normal stress is that the force is perpendicular to the failure area, usually a cross section. And in shear stress, the force is parallel to the area. I think that's all I've got for these slides. So this will be less than 30 minutes worth of lecture. I would like to record more. I may record more tonight. In fact, you know what? I'm going to go ahead and say that I will. So I expect you guys to watch all of these videos that I've shown you, plus go into the next one and watch at least, well, let's see, I guess I've got to figure out how much time there is, because the class is 2.5 hours worth, well, 2 hours and 20 minutes. So what I'll do is I'll just record enough information, probably the next set of slides or so, and I'll put them out and I'll turn on the next learning module as well. I expect you guys to go through all of that. I can't afford for this class to get behind. We've got to keep up with the schedule and get through the material so that we can do something fun, so we can do a project and learn as much as possible. So there will be more than just this video, but I have to stop now because I'm just about out of time. I've got to go to class, and it's a natural breaking point since we're at the end of these slides.